Okay, so want to talk about what the best angle is for this kind of polarization by reflection to occur. So we got this diagram sitting right here. Talk about this in just a minute, but I want to put some words into these fill in the blanks first. So in the diagram shown, an unpolarized, and I didn't give myself a big enough blank here, so I'm gonna write unpolarized incident ray. I guess I need twice the blank that I gave myself. An unpolarized incident ray strikes the boundary. And I'm going to use the word boundary, but we could have just as easily used the word interface between two media at an incident angle theta. And so here we go. This is our incident angle theta. Okay? And this is, if you like, this is the incident ray that's coming in, and here is the boundary that it's striking. Okay? This is the interface between the two materials. And again, of course, I have like an interactive app or something linked on the online platform, but this is just for paper, okay? Anyway, part of the ray is reflected, and part of the ray is refracted. This feels like 10th grade all over again. Something special happens. So if the angle between the refracted ray, I'm going to underline that it's the refracted ray, and the reflected ray is exactly 90 degrees, then all of the reflected ray is said to be horizontally linearly polarized. That's a mouthful. So really what we're unpacking here is the special condition that allows horizontal polarization to happen upon reflection, okay? So if I have light that shines in, and this light shines in like this, and I'm trying to set this up just like a ray diagram we would have had in grade 9, or grade 10 rather. The ray shines in. The ray reflects off. But what we never talked about in grade 10 was wave orientation. We just talked about it like it was, a ray, a straight path, right? But what we're saying here with these little arrows that you can just barely see is that the orientation of the light is up and down. And you can see those dots there. Those dots are meant to give the indication that I'll put X's as well, because remember we were using dots and X's as code for in and out of the page. There's there's electric field that's also wiggling in and out of the page. So what we're trying to say here is, and it's hard to draw in 3 dimensions, that the light coming in is unpolarized, right? But then when it reflects off, if the angle between, and remember it said between the reflected and the refracted ray. So here's my refracted ray. I have to add it in because it didn't copy very well on this paper copy. But here's my refracted ray. If the angle between the refracted ray and the reflected ray is exactly 90 degrees, there's my 90 degrees. That is not the incident angle. That is not the reflected angle. The incident angle is this angle. The reflected angle is this angle. And the refracted angle is this angle. So when I'm talking about 90 degrees, I'm not talking about any of those 3 angles. I'm talking about the angle between the reflected ray and the refracted ray. Okay? This angle right here, which is not something we talked about in earlier grades. So this effect can be observed using polarized sunglasses and looking at reflections off of smooth surfaces such as water or glass. And I mentioned the idea of looking at, hoods of cars or looking at water at the beach or whatever, right? These horizontal surfaces show this pretty well. Now, the thing is, typically, you don't get the light that gets through to your eyes from your sunglasses to be totally blacked out, right? And the reason you don't get it to be totally blacked out is that the light reflecting off of the surface isn't perfectly horizontally polarized, because it's pretty rare for the sun to hit a horizontal surface at just the right angle for the reflected and the refracted angle to be exactly 90 degrees relative to one another. That's why you don't get total blackout with like a good pair of polarizing sunglasses. You just get it to be dimmed, right? But if you did want to get total blackout, you would have to have like that exact angle, okay? Now there's a name for that angle. Anyway, the geometry of the situation is quite similar and leads to the following analysis, where theta b, and actually really we should be writing this as theta subscript b. I have to go back and fix that little typo. That should be a subscript, is referred to as Brewster's angle. No doubt that's some dead person's last name. It always is, right? But we give a name to it. So whoever figured it out must have been a Brewster. And it's the angle at which all of the reflected ray is polarized horizontally. And so what I feel like I struggled to illustrate in this picture is that in the incoming ray, polarization is all over the place. It's unpolarized. The reflected ray, notice that I only have dots and X's there, so it's polarized in and out of the page. Whereas the transmitted ray is vertically polarized. I feel like I really struggled to communicate that, so I'm kind of communicating it orally. I had a hard time communicating it visually. If you can think of a better way, let me know, okay? Because I struggled with how to put that into a picture format. So that's why I got all these words here to help with the picture. In terms of what we see, if you shine light, this is all we see. All we see is a split in the brightness. It's a beam splitter, right? Because our eyes don't pick up on polarization. You'd have to bring in something like this polarizing filter to be able to see if a horizontally polarized versus a vertically polarized filter would block it out. Okay? We need to have an extra tool like this because our eyeballs lack that perceptive ability. Cool? All right, so here's the math. Now, this is something called Snell's law. And unless you had like a really enthusiastic grade 10 teacher, you probably didn't talk about this. Or maybe you did. Snell's law goes like this. Sine theta 1 over sine theta 2 equals, and we have talked about this now, index of refraction, n2 over n1. And this is not a mistake. The indices 1 and 2 are in the numerator and denominator, respectively, on the left-hand side, and n2 over n1 is on the right-hand side. So I didn't flip those. That wasn't a mistake on my side, okay? So just so you know. So make sure you write it down properly as well. I'm going to put a box around this, and I want to like label the value so we know what we're talking about here. Theta 1 is the incident angle. Theta 2 is the refracted angle. Angle of refraction. Angle of incidence. N2 is the index of refraction. We talked about that previously. Describes the speed of light. In medium 2. And N1 is the index of refraction in medium 1. And all we said in grade 10 was that the incident angle and the refracted angle are different because there's a difference in speed. And what we said more recently, is that the difference in speed can be described using a coefficient that we call the index of refraction. Okay, so this is the ratio that describes like the mathematical relationship between how the ray will refract from one material to the next as it relates to that speed coefficient, that index of refraction coefficient. You guys are buying? All right, cool. Now, in terms of our specific diagram up here, when is this condition going to be met? Well, the condition is going to be met for perfect vertical polarization upon reflection when the ray diagram looks exactly like this. Theta I, theta R. Forget about the refraction angle just for a second. Oh, what the heck? Let's put in the refraction angle. Theta big R for refraction, little r for reflection. But the angle between the refracted ray and the reflected ray is going to be exactly, and I'll do it in a big, bold color, exactly perpendicular. And I might kind of make a note here that, notice, should we do it like that? Yeah, let's do that. Let's say that, should we express it that way? 90 minus theta b. Yeah, let's do that. So let's look at this. Theta r plus theta big R plus 90 degrees equals 180 degrees. Can we agree on that? That means that theta r plus theta big R, take the 90 over to the other side, equals 90 degrees. Right? 180 minus 90 is 90. So that means that, theta big R must be equal to 90 degrees minus theta little r, where theta little r is the reflected angle. True? And we also might make a little note to ourselves that theta little r, the reflected angle, is equal to theta incident. All true. So then we can make a small adjustment to this. The theta big R could be written as 90 degrees minus theta I. Cool so far? Now what we're going to say is that when this happens, we call theta I the Brewster angle, or the Brewster's angle. Theta B. We just rename it because it's like this special situation where this happens. And so we make a little statement. We say, okay, well then, if that's the case, theta R, we'll just rename things. It's not a big deal. Is equal to theta 90 minus theta B. So we can go back to our diagram. We could redraw it. Exact same diagram, really. We're just renaming things. Here's our 90 degrees. And we say, okay, well, theta I is actually going to be called theta B now, because it's the special angle where that 90 degree happens. Okay? And theta R would have the value that we just stated, 90 degrees minus theta B. Now that's nice because it relates theta R and theta B to one another, right? Or expresses theta R in terms of theta B. All right, so let's go back and do a little bit of math on this. According to Snell's law, so I know that some people are still writing this. I'll switch colors.
Is theta small r also Brewster's angle?
No. Oh, yes, theta small r is also Brewster's angle, but you notice that theta small r doesn't show up in the Snell's law, right? Because it's only the incident angle and the refracted angle. There's no reflected angle listed there, so I didn't really care as much about it, but it kind of helped me with my proof, you know. So let's go back. We could relabel this. We could say it. All right. Let's use these new labels. Sine theta. Instead of saying sine theta 1, let's call it sine theta b, because that's the incident angle, right? Instead of saying sine theta 2, we could call it sine theta big R. And I'm still going to call it N2 and N1. Index of refraction in material 2 versus index of refraction in material 1. But I'm going to switch things up a little bit. I'm going to say sine theta b is equal to, instead of saying sine theta r, I'm going to say it's sine of, I'll write it in red so that it pops a little bit, 90 degrees minus theta b equals N2 minus N1. Now, people that are really keen on their trig identities and their unit curves will immediately recognize that a sine curve is exactly the same as a cosine curve, but offset by 90 degrees, right? So as soon as I write sine theta b and sine of 90 minus theta b, I've really just phase shifted my sine curve by 90 degrees, which effectively makes it into what? cos theta b, right? There's a nice little cute trig identity. And people say, well, why do we learn trig identity proofs? Cute little things like that. That's why, okay? Because it simplifies the world. Also, it's like nice little puzzles, right? But it really is useful in many circumstances. But as soon as I do that, another trig identity immediately pops out at me. Sine theta b divided by cosine theta b is equal to what? Tan theta b, yeah. See how that works? Phase shifting is useful. Trig identity is useful. N2 over N1. Now, what that means is that all I need to know is the index of refraction of two materials, and I can calculate what angle would cause polarization. Okay? Let's put that in writing, like how this is useful or what this is useful for. Allows us to calculate what incident angle will cause reflected light to be 100% horizontally polarized. And sometimes a drag of like a lesson like this is that it takes a while for it to sort of get written down and to get talked out or whatever. But I honestly feel like talking it through slowly lets it seep into your brain at like a human pace. You should go back. You should look up some YouTube videos that explain all this in a quick animation. I would really recommend that you do that. Go watch like a minute physics video, or go back and watch like a Veritasium, or any of the other ones that explain things so well. They'll explain it to you in like 5 minutes or less. And having seen it once at a human pace, you'll be like, oh yeah, that makes sense. Okay, like really do like go back and watch this stuff. I'm encouraging you. I'm not saying that this is like a fast, well-produced explanation. This is like a slow, I can swallow this kind of explanation. Okay, and so if it makes sense to you, that's good. But if you have questions, please ask. Does anybody have any questions? Does it make sense? All right, at least like the geometry anyway.